Hello everyone, welcome to this video tutorial. So today in this video we will design a rectangular microstrip patch antenna in HFSS software using variables. So before we design this antenna, we will calculate the dimensions of this antenna using an online calculator which is on website westernnec.com. I will give the link in the description of this video. So here you have to click this option microstrip patch antenna calculator. So first I will enter the dielectric constant. I will use FR4 substrate here. So dielectric constant will be 4.4 and the height of the substrate is 1.6 millimeter and the operating frequency is 5.2 gigahertz. I will design this antenna for 5.2 gigahertz WLAN band. Okay, click on calculate. So these are the dimensions of this antenna. This is the length of the patch and this is the width of the patch. So this is the interface of the HFSS software. So first we will click on this option new. So a new project will come. Then we will click on this option new HFSS design. So this window will come and here we will design this antenna step by step. So we will use variables to design this antenna here. Means we will assign variables to these dimensions of this antenna. So first I am going to design the patch of this antenna. Patch is a 2D plane. So I will take a 2D rectangle arbitrarily and here I will assign the color first. The color I will take yellow. Then I will assign the coordinates and the dimensions using variables. So say I am taking the length of the antenna as L. Okay. So here I will put L by 2. And y coordinate will be minus W by 2. And I will design the patch on the XY plane. So Z coordinate will be 0. And X size will be, and whenever you will enter this L and W, it will ask for the values of these variables. The variable you are adding here, it will ask for the value of this variable. So this is the variable L. So first you have to assign the unit type. So say it is length. And what was the length of this patch? The length was 13.19 millimeter. So I'll put here 13. Okay. Now I will assign the W. W is the width of the patch. So this is also length. Unit type is length, and the value of this width is 17.54 millimeter. Click on OK. So what will be the X size? X size is the length of this patch, that is L, and Y size is the width of the patch, that is W. So the patch is designed, and I am taking the length along the x-axis and the width of the patch along the y-axis. Okay. So the patch is designed. Now I will calculate the ground. Okay. So I told in my previous videos, generally we take ground leaving 3h distance from both the sides of the patch. Okay. So the length of the ground will be L plus 6h and width will be W plus 6h. So let's design the ground plane. This is also a 2D plane. Take arbitrarily a 2D rectangle. Then I will assign the color first. The color I will assign green for the ground. Now I will assign the coordinates and dimensions. So the coordinates will be minus L by 2 first and minus 3 into h. I am assigning the variable h for the substrate height, that is 1.6 millimeter. So y coordinate will be W by 2 minus 3 into h. And substrate height is h. And I designed the patch on the xy plane. So the ground will be below the xy plane. So it will be minus h. And h I have not defined, so it has H is also a length, so assign the unit type first, then give the value. Its value is 1.6 mm. Okay. So what will be the X size now? The total X size of the ground will be L plus 6 into H, and width will be W plus 6 into H. Click on OK. So your ground is designed. See? Okay. Now I'll design the substrate material. So substrate material is a 3D structure. So I'll click on this option, draw 3D box. So arbitrarily I'll design the box first. Then I'll assign the material first in this box. The material should be FR4 because I'm using FR4 substrate. So click on edit, type here FR4. It will show in the library FR4 epoxy. Click and select OK. And also I'll make it transparent a little bit for the better visibility of the ground and the substrate. Sorry, ground patch. Okay, so the substrate material I have designed. Now I'll assign its coordinates from here. Create box. So what will be dimensions? This dimension will be similar to the ground. So minus L by 2 minus 3 into H. Y coordinate will be minus W by 2 minus 3 into H. This will be 0. The X size will be L plus 6 into H. Y size will be W plus 6 into H. And Z size will be minus H. Okay. So see, the substrate material is designed. It is spanning from the ground to the patch. Okay. Now I have to design the feed line. So feed line I will design here along x-axis. So feed line is also a 2D structure. So take the rectangle first. Assign the color as yellow. Then assign the coordinates. So what will be its coordinates? It will be connected here with the patch. So here the x size is, the x coordinate here is L by 2. Is it? And before I design the feed line, I want to tell about the width of this feed line. The width of the feed line should be 3 mm. I have shown you why the width we take 3 mm for FR4 substrate. This is because of the impedance matching purpose. If you take the width 3 mm, it will give you an impedance of 50 ohm, and the port we connect with the antenna is also 50 ohm. So for impedance matching purpose, we'll take the width as 3 millimeter. Okay. So it will be minus L by 2. Sorry, it will not be minus, it will be plus L by 2 and the y coordinate will be WF. I am taking the width of the feed line as the variable WF. So WF by 2 and Z coordinate will be 0 because this will be on the same plane of the patch. Now it will ask for this variable WF, that is the width of the feed line. So assign the unit type first as length and then give the value as 3 millimeter. Okay. Now what will be the X size? X size should be 3 into H. And the Y size should be WF, that is the width of the feed line. So see, the feed line is designed. Now I will unite these two, okay, using this Boolean option. So for that, first you click the patch, then press and hold your control key, then click this feed line, then click this unite option. So this will combine this together. Okay. Now I'll calculate the port plate here. That is the excitation of this antenna. To provide the excitation of the antenna, we'll use a port plate here. So for that, we'll change the design plane first, because this plate will be in the YZ plane, so parallel to the YZ plane. So I will assign YZ plane first. Now I'll take 2D rectangle to design the port plate. So first I am assigning the color here as red. Okay. Now I'll assign the coordinates. The coordinates will be, this will be L by 2 plus 3 into H, and Y coordinate will be WF by 2, and Z coordinate will be 0. Now the Y size should be, Y size will be in this direction, so this should be WF, that is the same width of the feed line. The Z size will be minus H. Okay, it is designed. Now I will design the radiation box. The radiation box should include the complete antenna structure inside it. Okay. So radiation box is a 3D structure. So before that, you have to change this plane first as XY plane. So arbitrarily I have designed the box. Now I will assign the material. The material I will assign as air for the more practical results. Okay. Also I will make it transparent for the better visibility of the other portions of this antenna. Okay. Okay. Now I will assign the coordinates. The coordinates and the dimensions should be like that. It should contain the total antenna structure inside it. So it will be minus L by 2 minus 3 into H minus 10 mm. I leave a space of 10 mm outside the antenna. So this will be W minus W by 2 minus 3 into H minus 10 mm, and this will be minus H minus 10 mm. Now X size will be L plus 6 into H plus 20 millimeter. This will be W plus 6H plus 20 mm. And what will be the Z size? Z size should be H plus 20 mm. Now see, the radiation box is designed properly and it is containing the complete antenna structure inside it. Now let's check what is left. So design part is done. Now the boundary conditions, the excitations and the analysis setup are remaining. Okay. So first I will assign the boundary conditions. So for that, select the patch first, right click, assign boundary as perfect electric. Now select the ground. For selecting, you can rotate it like this. Now right click, assign boundary as perfect electric. Okay. Now I will assign the boundary of this radiation box also. This boundary condition should be radiation. Click on OK. Now I will assign the excitation. So I will excite this port plate here. For that, you select it first, right click, assign excitation. LAN port. Next, none, new line. Select the integration line from here, like this. It is defined. Click next and then finish. So excitation is given. Now I have to give the analysis setup from here. Add solution setup and give the same frequency for which you are designing the antenna, that is 5.2 GHz. Then assign the frequency sweep. I'm giving the frequency sweep from 1 to 7 GHz with a step size of 0.1, and also I'll assign the sweep type as fast for less execution time. So everything is done. Now I can run or simulate. Okay, so click on this option to run. So it will take some time, but I will fast forward. Okay, so the running is over. Now I will plot the results. So first I will plot the reflection coefficient. So for that, click on HFSS results, create modal solution data report, rectangular plot, select S parameter S11 dV and click new report. Now see, it is resonating near 5.2 GHz, but the reflection coefficient value is not proper. It should be below -20 decibel for the general operating of this antenna. Okay, so this is happening because of the impedance mismatch. So for impedance matching, you have to do a little modification in the design of this antenna. So here you have to cut two portions from here and here for inset feeding. In case of microstrip line feeding, the impedance matching is done by giving inset feeding. So I will design two rectangles here, two small rectangles, one here, another one here. Then I will cut these two from this patch, so it will create an inset feeding. So first I am going to design, and before designing I will disable this radiation box first, because this will create problem in designing those rectangles. So for that, you click on this option and I will hide this radiation box to make the design easier. Okay, so click on this option, and before you design, you need to clear the solution, because we have already solved, so you need to clean up the solutions. Okay, now click on this option and design this rectangle. So what will be the dimensions of this rectangle? So it will start from here and it will span like this. So first I will assign this vertex. So what will be the coordinates of this vertex? This will be L by 2 plus 3 into H, and the width will be minus WF by 2. That coordinate will be 0. Now what will be the X size? X size will be the depth of the inset feeding, and I will assign a variable here also. So I will take this variable as P. Okay, so this will be minus P, because the spanning will be in the negative X direction. That's why you have to put here minus P. Now it will ask to assign the value. So P is also length, unit type is length. So I'll assign this value as 4.8 millimeter. You can choose this value by parametric analysis also. I will show this in my next video. Okay. So after parametric analysis, I have decided this value for proper impedance matching. So this is 4.8 mm. Click on OK. What will be the Y size? This will be, I'm taking as 0.5, and this should be minus 0.5. So this is actually the gap, the width of this gap here. So one thing here, it will be only L by 2. Okay. Now I have to design another rectangle here, but I will not design again. I will make a duplicate of it by selecting it and right click. Click on this option, edit, duplicate along line. Edit, duplicate along line. Then select any vertex and drag it to select a line. Select how many copies you want. Okay, so it is copied, but I have to modify its move vector. Okay, so for that I can edit the move vector from here. Duplicate, double click on this. So from here you can change the move vector. So the move vector will be 3.5 because this is 3. That is the WF variable plus this gap. So it will be, and the change is being done on this Y direction only. There is no change X direction and Z direction. Okay, so only Y vector you have to give. So this will be WF plus 0.5 mm. Okay, now I will subtract these two. For that you select the original patch first, then press and hold the control button, then select these two small rectangles, then click on this boolean option, subtract. So this will subtract these two from this original patch. So you can see this is the insert padding of Microstrip. Now I will again unhide this radiation box and I will simulate this again. Click on this option. So it will again take some time. I will fast forward. Okay, so the running is done. Now I'll plot the results one after another. So reflection coefficient is already there. So let's see. Now see, there is impedance is properly matched. You can see the reflection coefficient value is now below minus 30 decibel. And what is the bandwidth? You can calculate from this minus 10 dB line. You can note down the frequency of here. You can note down the frequency of here also. Then you can subtract these two and calculate the bandwidth easily. Here I am getting the bandwidth about 300 megahertz. Okay. Now I'll plot the radiation pattern also. So for plotting the radiation pattern, first you have to assign the radiation setup. So I'll assign the far field setup, infinite sphere. The phi value should be from minus 180 to plus 180. The theta value should be 0 to 360. Click on OK. Now click on this HFSS, results, create far field reports, 3D polar plot. Select gain. You can plot directivity also. Now I will plot only the power gain. Okay. So gain total, then select dV. Okay, click on new report. So this will show the radiation pattern, the 3D radiation pattern of this antenna along with the peak power gain. So the power gain is coming here 4.5 decibel. Now I will also plot the 2D radiation pattern. So for that, click on HFSS, results, create far field reports, radiation pattern. Now first I will plot the H-plane radiation pattern. So for H-plane, click gain total, then dV, then click on this families. So for H-plane, you know the phi value should be 90 degree. So click on here, uncheck this and select only the 90 degree value. Okay, then click new report. So you will get the H-plane radiation pattern. Now I will plot the E-plane radiation pattern also. For that, like the same way, click on results, create far field reports, radiation pattern, gain total, dV, and this time you select phi as 0 degree because for E-plane you have to choose phi value as 0 degree. Click on new report. So this is the plane radiation pattern of this antenna. And also you can calculate the other antenna parameters from here. For that, you come here and on this radiation option, you put the cursor and right click. And here you can see so here you click radiation, then this is the infinite sphere setup which we gave. Now right click on this option and click here compute antenna parameters. So this will show you all the antenna parameters, the efficiency, the incident power, front to back ratio, everything you can see from here. And all this will show in that solution frequency 5.2 GHz. If you want to see all these parameters for some other frequency, you can also see. For that, you have to click here and you have to change this option as sweep. And after selecting sweep option, you can easily change the frequency from here. You can choose any frequency in that sweep and you can calculate the antenna parameters for any frequency. So say I want to see the antenna parameters for 3 GHz. So I'll choose the 3 GHz option from here. Click on OK. Okay. Now it will calculate the antenna parameters for that 3 GHz. So you can uncheck this option. 1 GHz is by default selected. Uncheck and select only one value at a time. Click on OK. So these are the antenna parameters for this 3 GHz. So thank you for watching.